Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to start into the actual definition of the derivative, but we're only going to focus on the derivative at a point. There are actually two definitions we're going to deal with in this course. One would be the definition of a derivative at a point, which is this definition you see right here, which I'll talk about in a moment. And then we'll talk about the general derivative at any given point. They're kind of the same thing, to be honest with you. All right, so let's take a look at this definition. Short video just for the definition itself. The derivative of a function f at a point A. Well, that's denoted with this notation f prime is what we'd call that. Let me actually write that down. So we call it f prime at A, and that is defined to be, guess what? The limit of the slopes of the secant lines. Basically, it's the slope of the tangent line. I'll even write that down. It's the slope of the tangent line at x equals A. So all this time, when you work through algebra and you're working with equations of lines, and your instructor was saying, okay, find the slope of this line, find the slope of this line, find the slope of this line. The entire time your instructor was probably thinking, that's the derivative, that's the derivative, that's the derivative. Like, it's calculus you've been dealing with all throughout mathematics. However, I do want to tell you, slope is reserved for lines only. So the word slope, that is. So a curve, we do not say that a curve has a slope of whatever. We say the curve has a derivative of whatever, because the derivative of the curve at a point is the slope of its tangent line. So just letting you know, lines have slopes, curves have derivatives. Something that is kind of critical to note here is these last little four words, if this limit exists. That's kind of the caveat through all of calculus, is that most of the theorems and definitions that we hold to be true are such only if those limits exist. So if the limit does not exist, then the derivative is not defined at that point. So you do have to be very aware of that. So I think I've been trying to keep the videos much shorter. So I think what I'll do is I'll exit out of this video, and then the next video will be examples using the definition of the derivative at a point. I guess I can burn a few more moments here just to make this video worthwhile. So let's go ahead and visualize the derivative at a point. Again, I want to find the derivative at this point a comma f of a. That's my anchor point. I can move that a any which way I want. I could move it forward or backwards. I'm just not going to. I'm going to keep it at 1 comma 0 for purposes of this video. And what I'm going to do is, again, the definition just says, oh, I have this f of a plus h minus f of a all over h, and I want h to tend to 0. I want to take that limit as h tends to 0 and see if that becomes something finite, and if it does, that will be my derivative at the point A. So I'm going to let h here, and this is where I'm moving h. I'm going to let h approach 0. You could see what that does to the secant line. It starts dragging that non-anchor point, which is a plus h comma f of a plus h. It drags that closer and closer and closer to f at a. Now I don't want to have it touch, because if I had it touch, then the h would be 0, and you'd have a division by 0 for your derivative, basically, of your slope. But if h is really small, I mean really small, if h is like really, really close to 0, then this f of a plus h minus f of a all over h is an approximation of the derivative at a. Now here's the deal. these distances, I have a step size set up for 1/1000th, but for some reason it's just not quite working here. So it only does 1/100th step size, which is very sad because I'd love to see that 1/1000th step. But anyway, we can see that the derivative is roughly a -2. It's a -2.3 on one side, and if I let h be -0.01, you'll see that it's the derivative is roughly -1.97. So halfway between those two is about a -2. So we think the derivative is -2. Now, that should be okay with you because the example we just did in the previous video, using that same exact function, showed us that the slopes of the tangent lines were -2, or is -2. The slope of the tangent line at x equals 1 is -2. And we've just said that the derivative is the slope of the tangent line at that point. So that kind of matches up.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.